So in this course, some of this probably you might have heard of it, many, but just hang in there.
Okay.
You know, so it's a good idea that I review this.
Yes.
In this course, what we want to do is, when we don't have the outcome variable, okay, when we don't have the dependent variable,
Okay.
both mean the same thing. When we don't have outcome variable or the dependent variable, how can we do analytics? Because sometimes we don't know what is the dependent variable.
Okay.
We just have a blob of data. That means just a collection of data rows. Okay. Remember, each row refers to an experimental unit, and columns refers to the attributes or variables. Okay. So in a structured data set, that's what it is. Okay. So we are still talking about structured data set right now. And here are some examples. Okay. And for example, I would say list of topics is, for example, we have, let's say, collection of birds. Okay, we know that beak size, how many talons are there. Talons is the nails, right? In a feet. How many nails are there? Is it a long tail, or what are the color combinations are? Is the eyes, how big it is, the overall size of the bird, overall wing size of the bird, all these things, but given this information, can you group them into specific types of birds?
Yes.
So there is no dependent variable. Okay, so we are just grouping it. Oh, these are all like eagle class. Okay, these are all honeybee class and things like that. Okay. So based on the characteristics, we can still group them and get intelligence out of it, because oftentimes that is very useful information. Okay. So when we don't have, so such a grouping is called clustering. Okay. And we also want to know, we have too many variables, hundreds and hundreds of variables, reduce it to essential variables, principal variables. They are called principal component analysis. Okay. Principal component analysis. So this is a dimensionality reduction. This is grouping, but in a way you can see this is also dimensional reduction. Okay, a whole collection of variables are reduced into one variable, which is a nominal variable. This group 1, group 2, group 3, like that. So this is also dimensional reduction. So broadly speaking, that's where we are going. Okay, how to reduce the dimensions when we don't have any other information to essential information. Okay, and then the principal component analysis is grouping. That is also a grouping based on essential dimensions. Okay, grouping as based on essential dimensions. Okay, you can call it, that is also grouping, right? Grouping based on essential dimensions. So it's again dimensionality reduction. Okay, in that sense. How about factor analysis? The factor analysis is the dimension reduction, grouping based on hidden dimensions. There are no dimensions, directly that you are using it. You are using observations, rows and columns. Rows are observations, columns are attributes, but we are not grouping on the basis of the attributes, observed attributes, not based on observed attributes, but hidden linear attributes. Okay, that's what we are talking about. Okay, does that make sense?
Yes.
Yeah, good. So factor analysis, and then what happens is recommendation engine, right?
Yes.
There also we are talking about, there are limited information. So usually, there are, let's say there are products and then the characteristics, like for example movies and then the characteristics of the movies. Okay, and we want to know movies, let's say the movies are columns and then the rows are the people who watch the movie. So based on the movies you watched by individuals, we want to recommend a right movie to a right person. Again, we don't know, right? We are just talking about recommending something based on groups of information, groups of people's information to new people who look like them. Okay, so this is called recommendation engine, also called look-alike, right? Yeah. I mean, many of them are look-alike, but here it is very explicit. Okay, look-alike recommendations, look-alike, look-alike recommendations. Okay, you can call it as look-alike recommendation. So these are all the problems which we do in what is called unsupervised algebra, because there is no supervision here. Supervision refers to the outcome variable. Dependent variable is called supervised information, and there is no dependent variable here. Okay. And each, I mean, this is a huge topic, clustering itself. Okay, and principal component analysis, factor analysis is a huge topic. There is all, and then recommendation is a huge topic, right? But we are going to do essential thing. There is also, I will put it here, is discriminant analysis. Well, I mean, we know the outcomes there, so we don't want discriminant. But the, what is it called? The correspondence analysis. So here we have all the variables are, it's basically contingency table. Okay, all the variables are qualitative.
Okay.
Contingency tables. You can also call it as for contingency table. Okay. So in fact, this is also kind of contingency table, isn't it? In a way, if you look at it, but we have it row by row data, but this is summarized data. Contingency tables are summarized data. Remember, summarized tabulations. And here it is not a summarized data. It's one row. Each row refers to individuals. Each column refers to the products. Okay. In the case of Netflix, it's the movies. So these are the kinds of problems we are going to solve in the list of topics in unsupervised algebra situations. Okay. Now, so we have data sets that we will use, and what I wanted to do before we go further is I want to show you how to visualize data in multi-dimensions. Okay, so that's what I'm going to first talk to you quickly. So I'm going to use R to actually show you the visualization in multi-dimensions. Okay, but we are not going to do multiple dimensions, but two variables you know how to visualize, but how do we visualize in three variables? That's a kind of problem now I want to share with you. Is that good, everybody? So is Sharanya here? Not, oh yeah, she did join.
Yes, sir.
Okay, all right.
Yes, sir.
Okay, so let's consider the iris data set. You all know iris data set. That's the Fisher flowers, right? Three types of flowers. Yeah, three types of flowers. Okay. So if you want to see what those flowers are, the flowers are the following. So images. So these are the three types of flowers that we are talking about. Okay. Do you see this one? This is Iris versicolor, Iris setosa, Iris virginica. Can we allow machine to separate out this one? That's a classic classification problem, isn't it?
Yes.
That is, I teach it in the supervised algorithm, because we know that there are 150 observations that are there, and each observation, we know whether it is a iris versicolor or iris setosa, iris virginica, and then we have their measurement. So it's commonly available in R. So I just have to say, let's see whether it's already loaded. It is loaded, okay? So if you look at it, you can see, let me do it one more time so that it's spread out correctly. So here you are, yeah, okay? So there are 150 observations here, right? 150 observations. And then each observation, it gives me 4 measurement, sepal length, sepal width, petal length, and petal width. And it tells me that particular sample, is it setosa, versicolor, or virginica, okay? So the first 50 observations are setosa, that's what it is happening here, okay? First 50 observations setosa, next 50 observations are versicolor, next 50 observations are virginica, okay? The last 50. So it will start with 101, okay? Everybody's good so far about the data set?
Yes.
Okay, it is very important to understand the story of the data. If you are going to analyze it, you have to know the story of the data, and this is the story I'm explaining. So the problem here is, let me go back. So the problem here is that, this one, okay, the data is available here. The question is now whether we can classify this based on these measurements. So this is called sepal. You see this one? I'm going to, let me see whether I can copy image and then put it here, maybe a list of data sets. This is for visualization only, okay? Visualization, 3-dimensional visualization, 3D visualization. For that purpose, I'm going to use this one, 3D visualization of Fisher iris data. And I want to put it here, the image, okay? You see this one? So here, this is for visualization and classification, right? Usually classification, but I won't talk to you about classification today. So this is, there are, you see this one, 1, 2, 3, 4, 5, 6 of them are there, right? 3 and 3. Are you able to see that no, the petals are below the sepals? Everybody understand what I'm saying?
Yes,
Sepals
sir.
are below the petals, right?
Yes.
Yes, sir.
And so in all these flowers, that's what it is. Okay, petals are below, sepals are above. Okay, and using the information between sepal sizes, width, this is width and this is length. Okay, this is width, this is length, and this is width, this is length. You can see that this is a much bigger width, much bigger length, right?
Yes.
But if you look at this one, also much bigger width and much bigger length compared to this one, of course. Okay, but the relationship between them is very different. You can see that. Okay, because for example, the length is much longer than even perhaps this one. Okay, in the same way, this one is also. In fact, this is crazy, isn't it? Virginica has the petals are very big, isn't it?
Yes.
All of them are same class of family. But based on this measurement information, the machine will be able to classify, right? But today, I want to really visualize them, the data in 3 dimensions. Okay, that's what my purpose is. Okay. So there is a package I'm going to use, RGL, CAR. It is available. This library has certain, certain visualization. So I'm going to use it. Okay, so I'm running it, check the head, whatever I done. So I'm going to shortlist the name, give a shorter name for this one. Sepal length is iris sepal.length. I call this SL. SW is sepal width. Petal length, petal width. Okay. 4 variables are only there. Yes. Okay, so let's give the short name. Now I am ready to plot. But if you have 4 variables, there are many possibilities in 3 dimensions. You can combine sepal length, sepal width, and petal length, drop petal width. Like that, when you drop one thing, you get 3, and there are 4 possibilities. Everybody is good? There are 4 different ways you can see in 3 dimensions. 4 dimensions is very difficult to say. It's harder to imagine. Even 3 dimension is hard. So let's use the computer to do that for us. So from the CAR library, I have something called scattered 3D. Okay. It's a 3D scatter. You can do that for your analysis also, whatever you are doing. So I'm doing only the first one, isn't it? Is that correct? Something happened to this. Okay. So I'm using only sepal length, sepal width, and petal length. Okay? Only those 3 dimensions. X, Y, Z's are, sepal length, sepal width, and petal length. And I'm also grouping them using species. That is the iris dollar species. That means that the last column will identify them by the color, grouping color. That's what this one is. So let's do this. Okay. So here is the output. You see this one, I call it as 3 dimension because this is PL, petal length. I'm not sure whether you're able to see, this is SL, sepal length and sepal width. Then I can move this one, I can see, rotate this one, I can see this. That is the beauty of this graph. So what is the benefit of this graph? You can, from classification purpose, you can see that obviously there is a very clear separation here, between this class that is Virginic, I think it is, yeah. So we need to understand which is Virginica and which is the 3 classes, right? Virginica, versicolor, and setosa, right? But we'll come to that one. But the main point here is you are able to see this in 3 dimension, 3 variable, 3 dimension. You can rotate and visualize. That is the beauty of this. Okay, so you need this kind of visualization also for your work. Okay, to convince people, to confirm that you are able to convince people and so on. It is important. Okay, we can use this even in PCA also. Okay, but we will come to that later. So we want to also group them by name. Let us see what happens in the next graph. Ellipsoid to surface false, groups iris. So I'm doing the more of that work again. Okay, let's just quickly go through this one. Yeah, here the grid is false, ellipsoid true. That is, ellipsoid is giving us so some kind of a coloring, overall coloring is given. The green one is Virginica. Okay, it clearly points out there, Virginica. This is versicolor is this pink, and setosa is the purple, the blue color. Okay, purple blue. Okay, isn't it useful to view the data in 3 dimension, rotate it, and so you can see actually where the separations are happening by looking at these kinds of things like this. Okay, so I see a separation here, but we know that separation is going to be a plane because it's a multi-dimension. It's a plane, and there are going to be misclassification. You cannot avoid it. Okay, depending upon where the plane is. I don't think I can draw it.
Overlapping a little.
I'm sorry.
Are they overlapping a little?
Yeah, there is some overlapping is a little bit, not, but here no overlapping at all. So in any of the algorithm you do in classification, this is going to be 100% accurately classified.
Yes.
But here there's going to be some error here, 2 or 3 or 4, the maximum.
Yeah.
Okay, depending upon the type of algorithm.
Yeah.
That's exactly what is going on. Exactly. Did I answer your question or comment, Nini?
Yeah.
Okay. Yeah, there is some overlapping is there. Okay, because it depends on however you do a great job. So let me copy and post it in let's say, it should be able to copy here, close it, and then it goes back, plots. Oh, I should have done it. I closed it. Okay, so let me rerun it. There is a way oh, you know what? I cannot. I have to take a screenshot. I cannot store it. Okay, so I will rotate it in a certain way and then take a screenshot. Okay, which is a very different approach, right? I have to go and snag it here using my app. So I do that, copy. Now I can potentially in PowerPoint, I can potentially add a slide, and then I will clear that out and then paste it. Now, oh, not this one. I thought I took a, oh, I should go back and I know what to do. Go back here. I should copy this again. So now, I can show you what I'm saying. Like there is a plane. When I draw a line, think of it as a plane. Okay, that means it's a sheet.
Mm-hmm.
That will be the separator. Okay.
Yes.
And you can see 1, 2, 3 misclassified, and on that side, I think probably 3,
4, maybe
3 or 4, yeah, depending upon a little bit. I come in. I mean, this is just a visualization. Okay, you need math to be perfect, right?
yes.
Okay. Maybe this is what it is, right? 3 on that side, 1, 2, 3, 4, 4 on this side. Okay, something like that. Okay, I really don't know. Maybe I didn't rotate it perfectly to put a line like this. Remember, this is a plane. I keep telling you, right?
Yes.
This is a plane. That's a sheet of paper like that.
Yeah.
Okay, so this kind of information you need, rotation of axis and so on in this particular so unsupervised algorithm. So we wanted to get this kind of little bit of visualization into our thinking. Okay, so let me go back. Let's do a little bit more. We can do many things with this. There is also, let me do this again. Let's do a different set of 3D plots. So we can also do regression plane. Let's run this one. So that is coming. Just you do this one, it comes out to be regression plane. Do you see this one?
Yes.
It's a regression plane. Okay. Each class has a regression regression surface.
Okay.
Fit for that. Okay. This is what I call it. The middle one is a kind of, even though it looks like a line, it's a sheet. It's a plane. And that's what I call it as a plane. Okay. This is a plane. This is it's also called a plane. Okay. Plane, of course.
Mm-hmm.
Similar to aircraft, but then this has a different meaning in mathematics. So this is a regression plane. You can get it. Sometimes it's useful to explain, right? Visualization is to explain. Remember that. Huh? The other interesting thing, important thing in visualization is pairwise plot. When you have multiple variables, you want a pairwise plot. So I'm going to use this time ggplot, and then there is a command called pairs. Okay, and again I'm using the iris data. Okay, only iris data. We can do that with any data. So if you look at the pairwise plane, pairwise. See, for that one, I needed RGL. RGL is the one that helps rotate, okay? But this, it's not an RGL issue. It's just a two-dimensional visualization for us. So it is, the row is, for example, the whole row is interacting with the rest of the variables. That row is sepal length. And it is this correlation, the scatter plot is sepal length and sepal width plot. This is sepal length and petal length plot. This one. This is sepal length and petal width plot. Everybody understands that? How to interpret this?
Mm-hmm.
Yes, sir.
Okay. And how are you, Sharanya? Are you able to hear me?
Good, sir. Yes, sir. How are you, sir?
All right. All right. I'm fine. You're not speaking. That's why I'm trying to get your attention. Okay.
Sir,
Did we wake you up early on a Saturday?
Sir, that's not a problem, sir.
Okay. All right. So, what is this, for example? Somebody can, Nini, you know it, so I'm going to ask, what is this one? What is this plot, Gaushali and Sharon? What is this pairwise plot? It is scatter plot between what and what?
Scatter plot between sepal width and petal length.
Petal length, yes. And I want Sharanya to answer now. What is this one?
Sir, that's a scatter plot between sepal length and petal width.
Excellent. Gaushali, this one.
Yes, sir. This is a scatter plot with the sepal length and the sepal width.
No, this one I'm saying. Do you see where my arrow is? Okay, go one more time. You said sepal length.
Okay, sepal width and
This one. It's an interaction of the row versus column. So sepal width is correct. Okay. And then what else is interacting with what?
petal width.
Petal width. Exactly. So the other thing is this is symmetric. Do you agree with me? Because the scatter plot symmetric in the sense that it is meaning the same, but it is mirror image. So of the diagonal. So look at this one. This is same. Do you agree with me? The only thing is that it's a switch. It's an image, mirror image. Do you agree? See, this became here this. This became here this. Do you agree? So it is not different in that sense. That's the way it should be, isn't it? It's, it is a scatter plot, okay, between two variables. So it is you can, whatever you learn here, you can learn it from here. That's what I'm saying. Do you agree with me, everybody?
Yes.
Yes, sir. Yes,
Okay.
sir.
All right. So let's continue to do a little bit more. You can do more. You can do more looking at this command here. Let's run this one. It is more richer, that's all, okay? It's more richer. Let me go and show it to you. Yes, do you see this one? Because it is symmetric, I don't need the same picture here, but if I can get extra information here, that would be great. And this is correlation coefficient. So it provides correlation coefficient. It provides also the same information in colors and so on, a little bit more richer, okay? So you can use these kinds of codes to communicate in your results. There is another version of it, pairs.panels. Okay, it's from a different package. This is this is just we define it. Somebody defined it. Wrote the codes. I just copy and paste it, of course. But here it is part of the pair. It's part of the library called Psych. Okay. Where if you ask for this one, it gives another rich pairwise plot. It also gives you some kind of a relationship. It tries to give you some relationship here. So if it is like this, it's almost useless, right? That's why it is minus 0.2 correlation, right? But if you see this one, it's a lot more linearly related. You see, absolutely, it's linearly related here, isn't it? So the petal length and the petal width are highly correlated. That's what this says. Okay? Positively correlated. Everybody is good? What I mean, and not only that, it also gave me the histogram here about each of those variables. Okay. All right. Independent variables you can say, even though there is no dependent variable, you can say if you want, but really, it should not be misled to the idea that this is a supervised algorithm. It is not, because we don't have any information. Oh, in this case, sorry, I take back one sentence. Because this iris data, I'm talking about this particular course, but because it's iris data, we know these are all classes. Okay, so there is a dependency is there. Okay, and then I want to get your attention. Very important point that I taught you for Gaushali and Sharanya. Under what is called supervised algorithm, I also taught you some matrices. Agreed?
Yes, sir.
Okay.
Yes, sir.
Very good. So you know what is in the matrix, what is the Y matrix are useful for solving equations, right? And you know what is meant by row operations. Am I correct?
Yes, sir.
Very good. Very good. Very good. Excellent. The row operations are the easiest way to get solutions, right? And in the process, we also know how to get matrix inversions, inverted matrices or matrix inverse. Okay. And because mathematically it's useful, we will come to that, use it later on and so on. But what I want to get your attention is what is called the eigenvalues. Okay. Which I don't know whether I taught you in TA1 or not. Okay. The supervised algorithm or not. But we know how to define a matrix. Okay. So what is CA? I don't know. Let's see. Yeah. Okay. Yeah, it's a matrix already defined. Okay. This is the matrix I defined because in this example, I will want to show you. This is the example about the children. No, not this example. It's just an additional example to calculate what is meant by eigenvalues and eigenvectors. Okay. So if I do eigen, there is a command called eigen. There is something called eigenvectors and eigenvalues in mathematics, okay, in matrices. What it means is, it helps you to transform the original coordinates into another coordinate system, which may be a simply rotation, okay, Okay, I think before even I go there, I need to teach you this one, little bit of this one I'm going to teach, okay? I want to get your attention to this idea that the beauty of mathematics is that it makes many things happen, including the computers, okay? And one of the things in computers is, there are lots of different mathematics come together for computers to work for us, okay? But the one I want to, get your attention is matrices, because, if you draw a picture like M, like this here, this M, for various practical purposes, including games, okay? It could be, instead of M, this could be a character. And the character in a fight, for example, may become very big, or slanted, rotated, and it will do a flip, okay, and skewed like this. All these things, it will happen in no time, isn't it? In a game, okay?
Yes.
Do you all watch games? I'm talking about playing games in computer. You all do that?
Used to.
Used to, okay. How about
Not,
Gaushali?
not anymore.
Not anymore, you don't have time. Okay. How about Gaushali? Do you play games in the computer?
Yes, sir, we used to.
You do. Used to. Okay. How about Sharanya?
Sir, I play now also something, sir.
No, something. So the boss character will suddenly become huge. You cannot beat him because it's called boss character, right? I don't know what it's called. When my son was playing, you'll say, the boss has come now. The boss has come now. We have to fight him. He'll talk to me like that. No, I'll just watch him, what he's doing. So the boss character will do all kinds of, beautiful things, very powerful things. Right? He will become big, he will become rotate, he will flip, he will skew, his size will be skewed. The ordinary people, characters that don't know how to fight. But you have to fight. If you win, you get more points, right? But the point is not just the boss character. Every character will do all kinds of things, right? That is purely mathematics. That's where I'm going. It's nothing else is happening there, okay? It's just a purely mathematics that transforms this data into this data, scale, rotate, skew, okay? And scale, rotate, skew is done by matrices. That's my point. And here is an example. Matrices, look at this one. Let's say F is the character. For simplicity, F is the character, right? It's just sitting there. If you want to shift the character from, so many steps, you multiply this character by this matrix. That's all. All the points here, if you multiply by this matrix, then it comes like this. Do you get it?
Yeah.
Yes, sir.
All the points.
Yes,
all
sir.
the points. I'm sorry. Go ahead. Go ahead. You want to say something, Nini or Sharanya?
No, sir.
No. Okay. So instead of moving from here to here, if you want to scale, that is just basically bigger, right? This the shadow looks like the shadow, that is the small version. Scaled version is bigger version. You can even make it up to this. It all depends on how much W and how much H you give the values. Do you understand? If you want 10 times this, you give 10 10. 10 times it will become bigger, right? So all the original F data points should be multiplied by this, and it's very easy. Computer will do it, right, in no time, and suddenly it becomes huge. And that's what, and then you display that, the new values. You become the rotation is, there is something called sine function, cosine function. If you use it based on what angle you put, this original F becomes like this, rotated. Here is shear. This is called shearing. Shearing in x-axis. See F, how F became this F. And then if you want to only shear on the y-axis, you use this transformation. Okay, shearing is tan transformation, rotation is sine cosine transformation. And then if you want to flip it, you just multiply by this one. Multiply what? Multiply all the original points of F. Do you get it? Only F points. Okay, they're all points
Yes,
in
sir.
2 dimension, right? And then if you want to flip on both axes, you do minus minus 1. And that matrix, you special matrix, you will use it. If you want to only flip on the x-axis, you use this. Y-axis, you use this. That is what all about 3D the games are. Okay, I don't have to say 3D games, it's just, games. But it can be 2D games or 3D games, it doesn't matter. Okay? You all understand the beauty of mathematics here, and there is some references here and so on. Okay? So, given that transformations are done by matrices, that's all it is. You are transforming from one set of units of observation to another set of units of observation. That's all. Okay, and it could be more complex than these kinds of transformations. That's my point. This itself is powerful for games. Okay, but there are from one set of observation to another set of units itself will change. These units are not changing. Okay, units itself can change, and the units can be linear combinations of the original dimension. Those are all more advanced, right? That's where the eigenvalues become more powerful. Okay, so eigenvalues refer to the following. I need to introduce that one to you. So if I okay, the point, the question is the question is, if I give points in original and new coordinate system, okay, original and the new coordinate system, can I get back the transformer? Transformer is a matrix. Transformer is a matrix. A matrix transforms one coordinate to another coordinate system. What I am saying is that I give you points in one coordinate system, I give you points in another coordinate system. Can I find there is a matrix that transforms this to this matrix, the new coordinate system, isn't it? So can we get that transformer matrix? Excuse me. Is my question clear to you?
Yes, sir.
Okay, so get back the matrix, okay, that transforms all the points in one coordinate system to another points into another coordinate system, other points in other coordinate system. So it is possible as long as you have independent set of vectors in the matrix. Okay, in other words, so yes, there are coordinate systems. There is a transformer that will do it, and those transformer will do two things. One is it extends the axis, shrinks the axis. However complex, the most complex is a linearly constructed coordinate system using all the dimensions in the left side to the right side, which is the new coordinate system. Okay, so it defines new axis. So whatever the three axes we were talking about, for example, let's say here, this is the original axis system, and in this one it's the same axis system, but then it's a very simple transformer. It transforms all the points to the two-dimensional space. It's a three-dimensional space. It transforms all the points to two-dimensional space if 0 is always contained in that equation. Okay, so in other words, any point here can be transformed into a two-dimensional plane alone. Okay, or the full three-dimensional plane. The important thing is some transformations are so intricate, not complex, so intricate, they will transform the observations into linearly combined variables from here. It's not just transforming points to point, right? But it transforms them in such a way that it linearly combines all these variables into a different set of points in the new system, and we are going to use a mathematics to find such things. That's what is called the eigenvalues and eigensystem, okay, or eigenvalues, eigenvectors. So let me explain a little bit more with an example. So a matrix in original space means original space of points, right? Means it could be, remember, not necessarily three-dimensional. Okay, it could be 10-dimensional, 100-dimensional. Okay, still means it's a transformer of points to a new spatial relationship. How it defines new axis in the new space is the eigensystem. This is a very clearly defined simple word. Okay, simple sentence. How it defines new axis in the new space is the eigensystem. So, for example, so what I'm saying is, let us consider that the original data points are going to be transformed using the matrix. The original data points are x. Okay, it is going to be transformed by a matrix called A. Okay. Then what we are saying is that no, it is constructing in such a way that it is a scalar multiple of all these points. All the points are scalar multiples of all the points in the original system. It's a scalar multiples, okay, in the new system. Now, what we are saying, that's why it is saying scalar multiple of the original. So, whatever the complex transformation we are doing, it is becoming to be a scalar multiples of the original points. So, in this case, it's just a rotation, really, okay. So, what we are saying here is that this has to happen. We said in English, all the transformations that are happening by the CA is a simple scalar multiplication of of the new vectors. It's a new vectors we are talking. Okay, so which means it should satisfy this equation, which means it should satisfy this equation. Okay, everybody so far so good. And
Yes,
this
sir.
means it's a matrix set of equations. If the diagonals are subtracted by lambda. Okay, remember that matrix set of equations. Same as it is. One of the things we say is the determinant is 0. We don't usually use determinant, but in this case, I'm saying determinant is 0. Okay, because if you have equations equal to 0, so at least one of the values. When I say like this, that is equal to 0. This is also called in a special terminology. It defines a null space. Okay, because there is 0 here. So solution of null space for x. Solution of null space for x. Okay, we can say that way, or its determinant should be equal to 0. So determinant is there is a way to calculate determinant. There is something called adjoint method. I'm not going to talk to you about that. Don't worry about it. There are ways to solve equations of this type beyond determinant, but it makes it easier for me to say this. That's why I'm saying that it is equal to 0. Okay, because it's a small matrix, I can use this idea. So let's consider this example to explain this, what's going on. So in this example, I have an example called 2 minus 1 minus 1, 5. Okay, and so if this equation will become something called 2 minus lambda minus 1 minus 1, 5 is the matrix times x. So 2 minus lambda minus 1 minus 1, 5 is equal to 0, and determinant of that will be 2 minus lambda times let's see whether I have it here. Yeah, so this is what it is, right? That a minus lambda times x is equal to 0 means this is a, right? And determinant is this one, diagonals minus this one, right? Minus the product of this. Product of this minus the product of this is the determinant for this. In the 2 by 2, it is very easy. Okay, so far so good, everybody?
Yes, sir.
Okay, so this turned out to be a quadratic equation. Okay, and we know how to solve quadratic equation. The quadratic solution is this. Are you with me, Gaushali, on this one? Quadratic, how to solve
Yes, sir.
quadratic equation? Good. So the values are 5.3, 1.7. So if you plot that, what it says is that this equation, this line, this quadratic function, crosses the x-axis in these 2 points. That's what this means. 5.3, this 5.3, this is 1.7, this 5.3, something like that. Okay. Yeah. Remember, this doesn't mean that this is the 0, 0. This is 0. This line is 0. This may be a little bit away.
Dr. Sam, can you make it a little bit small because we can't see where you are pointing at the bottom?
We're a little bit small. Which one small?
Just make the
This one? Is this what you're talking?
yeah, or maybe just the PowerPoint page.
Oh,
so that
PowerPoint page
when
more
you
bigger.
are
Like this. This is the
pointing
best I
it-
can do. Oh, the
Yeah.
arrow. Arrow is not coming big. I don't know. I'll have to look into it. How to get
because
bigger
like
arrow.
when you're pointing at the bottom, we can't see because it's showing too big on my screen.
Oh.
I don't know.
So up to this is okay, right? The lambda values is okay.
Yeah. Okay.
And
I
on
think-
this direction, thank you. I'll try. I don't know. There may be some other way to do make it bigger arrow. Some way of making arrows bigger. I don't know.
I think I got it now. I think I fixed it on my end too.
Oh, okay. So I was saying these are the 2 points that came. I just plotted that, the quadratic equation, 9 minus 7 lambda plus lambda square. The values are 5.3, 1.7, which means it is, cutting the x-axis, horizontal axis at those points. Okay, that's all.
Okay.
I was saying this is not 0, 0. This may be 0 minus 2. Okay, because this has to be around something like this. I think it is something here, somewhere here. Okay. All right. Because yeah, it is correct. Why? Because when I put lambda, all these things 0, the y value is 9, right? So only if I have it here, it will cut 9. Correct. I was thinking about that. No, is it consistent? Yeah. Yeah. Am I making sense to you? That you have to be careful in interpreting plots sometimes. So it's telling that the real 0, 0 is around here. This is 0, 0. Because, this equation cuts y-axis when you put lambda equals 0, right? So it is 9. Approximately this is 9. Agreed, everybody? Approximately this is 9.
Yes, sir.
So this is 0, 0, okay? This is 0, 0. I don't want you to miss that point. That's why I said that. Okay. All right. So now that I found out lambda, they are called eigenvalues. I can find their corresponding eigenvectors by actually supplying that value and solving the equation. And you know how to solve this one. When I supply that first value 1.7, this is remember 2 minus 1, 1.7, minus 1, minus 1, 5 minus 1.7 times x is equal to 0. That's what it is, your equations are. This will give a solution, and that is your first eigenvector. This is your first eigenvalue. This is your first eigenvalue. Maybe it's better to put it like this. Okay, 1 second. Because it is the first value I was talking about. So this is the first eigenvalue, and then this solution, this matrix solution, and you know how to do that, row operations, right, everybody? Okay, so
Yes.
using that, you can get the first eigenvector. But of course, your computer will give you that first eigenvector automatically, right? And that is what is here. So when I call for eigen A, that's a function called eigen, it prints the eigenvalue 5.3 and 1.7. The reason why it gives 5.3 is that it automatically, sorts it and then gives you the first highest value. And it so happens in this matrix, all values are positive, right? When you go all values positive, it's called positive definite matrix. Your variance covariance matrix will all have positive values. Does that make sense to you? Because it's a variance covariance will have positive values. Eigenvalues and such values are, when you have it, it's called positive definite. So when you create a matrix of variance covariances, it is a positive definite matrix. Please write it down. Positive definite. One way to check it is using the eigenvalues. Okay. And then I said the first eigenvalue is this one. Its eigenvector is this column. Everybody gets it? Second eigenvalue is this one, and its second eigenvector is this one. Everybody gets it?
Yes.
Yes.
Okay, very good. And also a few other properties you can see, okay? And I'll remember that. So I'm going to call this and copy. You know why it is all of them are positive, because this is a positive definite matrix. That means you take any vector, multiply both left side and right side, it will always be positive. Any vector you take it. Okay. Can we do just a little bit of computation here? So one way to do that is a percent star. Percent is the multiplication. So any vector, can you give me some vector? I will put a vector here. And both left side and right side. If I multiply, it will be positive number. It doesn't matter however big negative number you give. It should be like that. Okay. So let's say minus 10, and whatever, minus 5. person star person. Okay, A times same thing, right? I think I have to have it as C. And then it should be C also here. Transpose of C. Okay. Minus 10. Same vector. Remember, that's very important. Okay. Because that's how it becomes a quadratic equation. Right? Non-conformable argument. I have to figure out. Maybe I should say matrix, right? So first I have to define it as a matrix. C1 is not there, so C1 equal to matrix. I'm going to define minus 10, comma, minus 5. Because I think you may probably would have figured out, maybe because both sides are negatives are coming, it will become positive. But then your matrix is negative, remember that, right? Your matrix is negative. It has some negative elements also. So we can't really say. It depends on some internal things that are going on, right? So this is my row 1. N row is equal to 1, okay? It should be good enough by row 2. I don't know whether we need that, but anyway, I'll write it. Okay, so let's try. Matrix A, right? Percent star percent A, percent star percent. Transpose of C1. Am I making sense to you? Do you know what I'm doing here, everybody? That is, I am pre-multiplying because it's a row, right? Row by column, so two values, okay? And two values are one after another, correct? You know what I'm saying? If you multiply 2 by 2 rows, no, 1 row by 2 columns, right? Times 2 by 2, what will it outcome will be 1 by 2. Agreed, everybody?
Yes,
1 by 2 times 2 by 2 is 1 by 2, correct? Is that correct?
Yes,
That's
sir.
the first part. That's the first part, right? Up to this is 1 row, 2 columns. This is 2 rows, 2 columns. So when you combine together, multiply, it becomes 1 row, 2 columns. And then this is 1 column, 2 rows, right? So because of this will be, how many numbers is this? It's just 1 by 1, right? 1 element, correct?
Yes, sir.
Everybody, Nini, you're good, right? C1 times the first part, C1 times the multiplicator, C1 times A. What is the size of that? That's what I'm asking.
Okay.
C1 is 1 by 2. Please write it down. C1 is 1 by 2. Okay. C first part is so 1 by 2 multiplied, right? Multiplied by 2 by 2 multiplied by 2 by 1. Correct, everybody? That's what we are doing.
Yes, sir.
So
Yes, sir.
if you do only up to this, what will be the output? I ask this question because we need to figure out all the time how many the resultant number of rows and number of columns. Always the resultant number of rows and number of columns. Okay, it's very important. So here I'm asking, if you do only up to this, the resultant number of rows and number of columns is how much? Anybody? Nobody's talking. Huh?
16, sir.
No, 16, no. This is 1 by 2 times 2 by 2. So, 1 by 2 means you are multiplying. Let me go back to this one. Nini, are you with me? Are you okay?
I'm like,
Okay.
I'm a little
So
behind.
I pre-multiply this by, let's say, minus 10. This is the multiplication I'm going to do, right?
Okay.
So
Yes, sir.
I'll do it once. Okay. So I'm going to do here a multiplication, pre-multiplication as insert row, insert matrix, right? Mathematics. Equation, matrix, let's see. I want matrix. Why not just the equation, I want symbol maybe? No, not symbol. What happened? Not insert. Insert. Math, not equation. I should have. That may be the issue here. There is no object. I have to go there to get the math. One more. Really? There is no math here? Graph is there? Okay, let's see. There must be somewhere here. Insert, zoom, shape, set, math, object. Usually it comes from the object, equation, symbol, video, screen. Insert the equation. I'm not talking about equation. Oh, okay. So you know what I'm going to do? I'll take this as one more time. Let's see what happens. Okay, I will erase some of them. No. So I'm going to do like this. Okay, minus 10, comma minus 5. That's what we were talking about. That's fine. Okay, this is what we are talking, right? If I do this multiplication, I don't have to put this star, but let's put the star so that it's clear to you that I'm multiplying. Minus, how do you do this? What is the answer? Come on, let's get it there.
So that would be
20 minus 20. Everybody should know this. Very simple, okay?
Minus 20.
Plus 5. Agreed?
Yes, sir.
Okay. First row, first column. And then first row, second column. So it is going to be like this. That's all I'm saying. First row, second column means 10 minus 25. Got it?
20. Yes, sir.
So what is the size of this? This is it. What is the size of this? Okay. So this is minus 15, comma, minus 15 and minus 15. Really? Okay. Very interesting. Correct?
Minus
Everybody?
15 plus. Yes, sir.
Everybody is good?
Okay.
Minus
Yes, sir.
10,
Yeah.
minus 10 times 2, minus 20, minus 5 times minus 1 plus. This is minus 10. So plus 10 is minus 5 times minus 5, plus 5, 25. So minus 50, minus 5. This is one row, two columns. This is the size. That's what we call it as the size of the matrix. When we say that. So what happened here? It's very easy to calculate that. This is 1 by 2. This is 2 by 2. So you remove the middle part. That's it. This is 1 by 2, isn't it?
Yeah, so now it becomes 1 by 2.
Yeah, exactly. This is one row, two columns. This is and it's easy to figure it out. You can do multiple things, but remove, as long as it's a consistently defined, you can remove them. That's all. Very easy, right? Oh, let me see. Font. I'm going to put here subscript, and I'm going to say, oh, I didn't want that. Control Z. So here I should say, okay, font, insert. Anyway, I don't know. It takes a long time, but let me finish it anyway, because I have come up to this. This is the problem of coming up to, okay. And you cannot give up also. So this is 1 by 2, isn't it? And this one is 2 by 2.
2, yeah.
This is 2 by 2. So what I was saying is, give me a moment. I'll correct this guy. This is supposed to be subscript, and the subscript doesn't go too far here for this one. Okay, it's not going to be a problem. Okay,
Maybe
don't worry about
you might
it.
have to give one more space.
So we got it now.
Yeah,
Yes,
we
sir.
can-
1 by
we can-
2.
Yes. That's
Connect.
okay. Yeah. So it's a 2 by 2. What I'm saying, this 2 and this 2 will disappear. That 2
Yes.
and this 2 will disappear. That's my main point. So your answer is 1 by 2. That's what this one is. This is 1 by 2. Isn't it? 1 row, 2 columns. But now what happens is you are going to multiply this with, what is this is the transpose of this, isn't it? Right? That will become a column. This will become a column when you do the transpose. When you do that, what happens? So both the negatives are becoming positive. You see this one, 10 by 15 is 150 plus 100 plus 150. This is plus 75. So 225, the answer, isn't it? If I multiply this by right side, the transpose of that. That's where I was trying to do here. This one, right?
Yes. Yes, sir.
So let us see what the answer is. 225. You get it? So it doesn't matter.
Yes, sir.
Whatever the number combination you give, a vector. This is a new vector. Remember that. This is any new vector you give, it will always become a positive number. That's why it's called positive definite. Okay. Now, and what is the interesting thing about positive definite? All its eigenvalues will be positive. Okay. And the eigen system of computation automatically, gives evaluates all the eigenvalues and then ranks them, and then always will give you the highest eigenvalue first, next highest eigenvalue second, and so on. Okay. Now here is the interesting thing. Okay. The eigenvalues, basically creates a rotation of axis. Okay, and in this case, this is the original data points. How they are, it's the original data points, right? In the original data points are in the x, y, z axis. In the x, y, z axis, these are original data points. But the eigenvalues, finds where the most of the observations are. So this is the principal axis. That's why it's called principal component. This is the principal axis. It has most of the variance in the data. Okay? Do you understand what I'm saying? So this axis, the data, if I make it easy for you to visualize it, to identify it, to associate yourself with this conclusion that, look, most of the variations are here. Next, most of the variations are here. Do you agree? Something like that is there, right? And then finally, most of the variations are this way. And interestingly, all of them are perpendicular. So it tells you, it rotates and then takes where the most of the data are. It takes our transform, the matrix, the eigenvalue system takes us to the most of the variances are. And it also tells you which axis is maximum variance explained, next to which axis is maximum variance explained. That has to be perpendicular. Okay, these are perpendicular systems. Okay, and finally because it's a 3-axis, so this is the final axis which has the least the variance explained. Does that make sense to everybody? That's what eigenvalue system does. Everybody's good? Very good.
Yes, sir.
Sharanya?
Yes, sir.
Okay, thank you. So, interestingly, also, okay, so you understood eigenvalues, eigensystem, okay? So, which essentially means, if I want to say, look, you know what, the third dimension doesn't contribute much at all. Essentially, first 2 dimensions is good enough. 95% of the variance is explained. Do you agree with that kind of statement?
Yes.
Excellent.
Yes, sir.
The lambda value itself tells you how much variance is explained. That is another thing. So one thing is that the lambda value tells you how much variance is explained in the multi-dimension context. And the second, and they are all ordered also for you beautifully. Mathematics does it for you. They are all, that tells you this is the axis by which most of the variance is explained. Next, it tells you next perpendicular axis is this one, and that is the one next most variance is explained. And finally, in a 3-dimensional case, third dimension is good enough. Third dimension solves the problem, and this is the one. And technically, you can probably drop this one, and sometimes even drop this one. 1 axis is good enough, or 2 axis is good enough, 3 axis is good enough. In given big problem, most of the time, few axes are good enough to explain the problem. That is what is called the principal access problem or principal component problem, principal component analysis. Okay. Now that's what we are going to do. We are going to find using eigensystem. You don't even have to think eigensystem, but if you ask for principal component, automatically it uses eigenvalue system, eigensystem, and then does all these things for you. It talks to you about how much variance, the first variance, what is the first axis? So how do you find the axis? An axis is basically a three-dimensional vector. One vector will tell you this point or any point on this line tells you what is that axis is. Do you agree with me? So the eigenvector connected to this one is the vector connected to the first eigenvalue. Do you understand what I'm saying? So I know the eigenvalues and the eigenvector. So I know the direction of the vector, eigenvector, which helps me to find the maximum variance explained axis. And how much maximum variance explained is also the length. This red line length is the one. Everybody is good?
Yes.
Yes, sir. Yeah.
Yes, sir.
So that's what we are going to do. So something I have to explain to you is that, what is the... So I explained what is an eigenvalue, eigenvector in terms of geometry. I explained how it is used in the data science also. Okay. So let us do, one thing I want to talk to you is about what is meant by variance covariance matrix and correlation matrix. Okay. Because PCA is about variance covariance matrix. Okay. And you can also say it is about correlation matrix, that's fine. Okay, both are fine. This is a unstandardized variables, this is standardized variables. Standardized variables means you subtract the mean and then divide by standard deviation. That's for all the variables. Then it's the standardized data. And if you calculate variance covariance for that standardized data, it becomes automatically correlation matrix. So how do we calculate variance covariance matrix? What does that mean? So that I want to explain now. Okay. So let me go back to this one. Variance covariance matrix is somewhere here. Okay. Two important square matrices in data science are variance covariance matrix and the correlation matrix. Okay, so let us say there are three variables, x1, x2, x3. So when you have two variables, you can calculate the variance or covariance between them. Do you agree with me? Not variance, sorry, covariance between them. Do you agree with me?
Yes, sir.
Yes, sir.
You can calculate variances, but it will be two different variances. There's a variance of x1, it's a variance of x2. But if you have covariance, it's only one. It is between x1 and x2. Because x2 and x1 is same as x1 and x2. Do you agree with me? Covariance between x1 and x2 is same as covariance between x2 and x1. Everybody agrees with me?
Yes.
Yes, sir.
Okay. Why do I say that? Take a look at this one. This is the covariance matrix. This is covariance between x1 and x2. Correct? But what is covariance between x2 and x1? It is the same thing. The only thing is that probably you want to change it to 2 here, 2 here, and 1 here, 1 here. But it is symmetric, it doesn't matter, so it is same value, isn't it?
Yes.
So covariance between x1 and x2 is same as covariance between x2 and x1. So nonetheless, covariance between, so if you have three variables, you can find out variance between variance of x1, variance of x2, variance of x3. You can also find out covariance between x1 and x2, covariance between x2 and x3, and covariance between x1 and x3. That's all you can do. Everybody good?
Yes.
And that is what this one is. That's what this one is. So you can say variance is same as covariance between the same. Covariance between x1 and x1 is variance. Everybody agrees?
Yes, sir.
Covariance between x2 and x2 is variance of x2. And it's very easy. You just put the x1 and x1 means you change it to x1, x1, it becomes square. That's what it is, right? 1 over n x1 minus x1 bar square. That is your variance. Correct?
Yes.
So the diagonals are variances, off diagonals are covariances. When you construct a matrix like this, it's a symmetric matrix, right? Because this value is same as this, because covariance between x1 and x2 is same as covariance between x2, x1. This is covariance between x3, x1, and so on, which is x1, x3. Everybody is good? So it is a symmetric matrix, and this is how you calculate the covariance matrix. Okay? And covariance matrix is a positive definite matrix. That should not surprise you, but I'm just telling you. So the benefit of what is the conclusion of what is the conclusion of a positive definite matrix is that this is all its eigenvalues are positive. Correct? Everybody?
Yes.
In a
Yes,
break
sir.
one man. You all need some break. Is that what it is? Not energy. I'm not feeling the energy from you.
Nope, I'm okay.
You're okay. You're okay. I know. Sharanya and Kaushal.
I'm okay too, sir.
You are also okay.
Thank
Kaushal, you need a break? A little bit of break, you mean? It will be better. Huh? Okay, go. 5 minutes. How about that? Remember, when you come back, you should be able to explain what is meant by covariance matrix. So don't lose that thought. 5 minutes break.
Yes, sir.
5 minutes
you, sir.
break. Okay.
Okay.
Thank you. I'll be here. Okay. So
Okay.
can you join? Thank you. Can you hear me now? I'm sorry. Can you hear me?
Yes, sir.
Okay. I'm sorry about that. 1 second. Sir. I was testing some idea now for present it through my.
Sorry, I'm back.
Okay. All right. Welcome. Okay. All right. Okay. I'm going to exit this one. Something happened. I wanted to see, editing is so complicated, no, in this one. That's why I wanted to use the iPad. But anyway, so you all understood what is meant by variance covariance matrix, right? This is what you do in the multi-dimensional case. If it is only single dimension, you just find out there is no covariance if you have single dimension, correct? Only variance. You have two dimension,
Yes.
there are two variances and one covariance. Okay. And it is a positive definite matrix. So your PCA is really about identifying principal axes, principal dimensions, principal eigenvalues and eigenvectors, which gives you your ability to explain most variance in the data. Am I making sense?
Yes.
Okay.
Yes.
That's what you are doing. Your principal component analysis is that's what it is doing. It is giving the ability to find out the most important axes. 2 or 3, that's good enough. In fact, we don't even use 3. Most of the time 2. For certain types of analysis, we may use more dimensions. But for visualization, we do only 2, not even 3. In fact, I teach our students, how to use 3-dimensional. Now you think about that 3-dimensional rotation, all those things. We can plot like that. What is called, 3-dimensional plot of the most essential axis, where most of the variance is there in the data. Am I making sense?
Yes, sir.
Okay. Nini, you're good, right? What is that statement?
Yes.
Excellent.
Yeah.
Sharanya, you're good, right?
Sir.
Okay. All right. So let's just do that, and we are going to do one answer, and we will catch on the idea. But in a sense, what we are saying is that now this is the fundamental theorem. Okay, that is a variance covariance matrix can be decomposed into that many number of dimensions, that many number of values, that many number of matrices. So each one is a first eigenvalue has first eigenvector, which is p by 1 matrix, p by 1 vector. Okay, p by 1 vector. So you can see, go back to that one. I could have read it this the other way also, because of symmetry, it works out well. Because of symmetry, where is the variance eigenvalue here? Okay, eigenvalue. Oh, here I was showing you here in R, right? If you look at this one, there is something going on here. I can say the vector is this way or this way. It doesn't matter, right? Because of the symmetry. Are you with me? Eigenvector is this way. So eigenvector is this, or I could have said eigenvector is this way. But it's the same because of symmetry. Okay. So what we are saying is that first eigenvalue, okay, it weighs the matrix. It is the weight you give for the matrix that is called the first eigenvector related matrix. That is first eigenvector times first eigenvector transpose. So eigenvector is p by 1 by p, multiply it, then the drop in between drops out, right? It's a p by p matrix. Agreed, everybody?
Yes, sir.
Okay.
Yes.
I know it is p because this matrix is p. It has to become p, right? So we are p by 1 and 1 by p. It has to be, right? So this is the first eigenmatrix. This is the second eigenmatrix. This is the third eigenmatrix. But the way it is done, matrices, it's just a special word I am using it. It's just a generated matrix using the eigenvector. First eigenvector times first eigenvector transpose gives you the first eigenvalue related matrix. Second eigenvalue times second eigenvector times second eigenvector transpose. That gives you 1 by p by 1 P by 1 times 1 by P, again P by P. So each one of these is a P by P matrix weighted by their corresponding eigenvalues. And how many of them will be there? There will be P of them will be there, because this is P dimensional. So it has to be P dimensional also, unless this is a some of the values are zero variances in the diagonal. Are you with me?
Yes.
Yes, sir.
I shouldn't say in the diagonal. There is some relationship between those variables. So, you know, one row is a linear combination of other rows. One row is a linear combination. In the covariance matrix, if one row is a linear combination of others, then the determinant will be less than, it will be 0, which means one of the eigenvalues will be 0. Okay, if it is exactly one relationship. If there are k relationships, you know, among those rows, k eigenvalues will be 0. My main point is, so this can be decomposed into matrices like this, weighted matrices like this. And the problem is, because lambda 1 is the highest and lambda p is the lowest value is irrelevant, most likely. The whole matrix is weighted down by this, right? So maybe it is irrelevant. Maybe it is relevant p minus 1 axis also. Maybe it is relevant p minus 2 also. So my point is, the most important thing is what matters. It may be top 3, top 4, or something like that. Everybody got an idea what I'm talking? This is where we determine how many, I know how many dimensions we need. How many dimensions are valuable in the case of your data set, your given data set. Okay, so this is about variance covariance matrix. And I also want to tell you about the correlation matrix. So correlation matrix is, you are dividing, I know, let me go back and explain that to you. Correlation matrix is that you are dividing each of the rows and each of the columns by its variance. That's it. Each of the rows and each of the columns by its variance. So somewhere here it is here. 2, 3, 2. Maybe down, no? Okay. Wait. This is the one. It should be really okay here. So if you divide by this row by x1, first row by x1, second row by x1, x2 variance, right? Not variance, standard deviation. You divide that. Then also the columns you should divide by their corresponding standard deviation. So second column should be divided by what standard deviation? First row you divide by first standard deviation. Second row you divide by second standard deviation. Third row you divide by third standard deviation. If that's the case, second column you should divide by what standard deviation?
Oh, x2.
Exactly. Standard deviation x2. Everybody gets it?
Yes, sir.
Sharon and Gershali. Okay. So when you do that, this becomes a correlation between x1 and x2. This becomes correlation between x1 and x3. This becomes correlation between x2 and x3. What about this one? This becomes 1. Do you agree with me?
Yes, sir.
Because you row-wise you divided by standard deviation of x3. Column-wise also you divided by standard deviation of x3, which becomes the bottom is variance of x3. Top is also variance of x3. This is variance, isn't it?
Yes, sir.
So it is becoming 1. Okay. All right. So correlation matrix diagonals will always be 1. All the other values will be less than, 1 and greater than -1. I remember that, right? But it's all correlations coefficients, right? So you can, it can be in the this is called decomposition result, right? Theorem, decomposition. This can be correlation matrix or it can be variance covariance matrix. It's the same thing nonetheless. So what is this one? This is called singular value decomposition. This is called eigenvalue decomposition. And I will teach you later singular value decomposition. The big difference is, this is about variance covariance, this is about data matrix. Wow, that is very powerful. What we are saying is that this kind of decomposition you can do even for the data matrix. That is exactly what we do in recommendation engine. So in one jump we talked about, but there is more complications here. I will come and talk to you about that, because you remember these are all, U1, V1. Here it is same, epsilon 1, epsilon 1. It's U1, V1, U2, V, U2, V2, like that. So there is something complications going on here. There are more vectors to find here than here, right? Here there are only p vectors to find at most. But here it can be data matrix, so it can be, 100,000, 10, 20 million customers and 100,000 movies, right? So it is a rectangular. It is not like this symmetric and nice, square and symmetric. It is very complicated. It's very ugly. It is rectangular, okay? But still, mathematics works out. That's the beauty of singular value decomposition. We'll come back to this. Just put that in your brain. So let's do one problem here about this. What happens, okay? So there are two problems here, right? One is to find out what are the most essential dimensions that are needed to explain the variance here in the data, multidimensional data. What are the most essential directions, or most essential directions which explains most of the variance in the data? That is the first point, right? The other one is, okay, this is in the original, once you get this eigenvalue system, you can use that system to transform it into the new data set, right? New coordinate system. So you can solve the problem, explain the problem in the new coordinate system. But you will only have few dimensions, that is abstracted out of the original dimensions into the new dimensions. Okay, so you need to find out how to identify the data points in the new data system, in the new coordinate system. How to identify the old previous data points into the new coordinate system. Very important, right? So that you can plot them and then visualize it to explain what are the essential dimensions and then how they explain the variance, which essentially means how they help us to group, the previous coordinate system values into new coordinate system values. So it is good if you can give intuitive meaning to your new coordinate axis. See, each of the axes here, income, age, it's all very easy to explain, right? But in the new coordinate system, it may not be so direct, but it may be interesting combination of insight. Am I getting across?
Yes.
It might be an interesting interpretation, but of course, the simplest interpretation is going back to the original data, but that's not useful to you to reduce the dimension and explain. So you still have to find some interesting meaning for each of the axes. That is called insight. Very, very interesting insight, right? But that only you will have to think about as a human. That is not something AI can do. We will see some examples, okay? So let's see an example. I'm going to talk to you about what is called places almanac. Okay, so here you can see this on GIF file, right? So you can see that it rotates, but you will see the maximum variance is explained when it finds this direction, right?
Yes, sir.
Oh, I want it to stop. It's not stopping. Okay. Yeah. Okay. I'll stop. So that's where it will stop. And this is the lambda. This length is lambda 1. I talked to you. This length is lambda 2. Okay. Right. This is just a fun GIF file. Okay, so this is what I want to speak with you. That is, I think the data is here. What is called places rated. Okay. So this is a very common, interesting example. Okay, there are 300 and let's go to this one. Places rated almanac. we have to go to a data set called eigenvalue decomposition, places rated almanac. Okay. It's actually here. Places rated almanac is, it's called places. The data set is places. One more. USA arrest analysis. I need to know the package name. Why is that it's made? Okay. Let us see whether by plot. All right, we will just I'll find out. It should be package. Data table mass. Okay, resolution data tables. Or data sets package maybe. Places. It's not a table useful commands data frame. I think it is mass. Let me see. I should not keep it that note somewhere. Okay. Library mass. Uppercase. Okay. It's not there. Okay. Somewhere that notes is missing here. I'll come back to places. Okay, I'm going to go down on this here. Page not found. Okay, here it is. Okay, to finding the best places. Compare series best places. Let's go here. Okay, so this is the data, okay? The places data. So you can see here 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this number index 1 to 329. There are 329 places in USA. This is the story of the data, okay? 329 places in USA. That is where the data are collected about how good in terms of the climate and terrain, how good in terms of the housing, healthcare environment, crime, transportation, education, arts, recreation, and economics. Okay, so it's a livability of the place. Okay? And this is the score that they collect among people, okay. This is the score value that collected the aggregated data they have here. And there are 9 variables, and these are the 9 variables, and for each of the 329 places. So this is the raw data. Okay, so you want to find out, if you want to do, think originally and understand all these things, then you are really talking about finding an eigenvalue for the covariance matrix. Everybody understands? There is a command called COV, which gives you covariance values.
Yes,
if it is a multi-dimensional data, it will be covariance matrix. Yeah, go ahead, please. Say something.
No, sir, I say yes.
Oh, okay. So I'm going to read that as a places. So I'm going to download that, and maybe it is somewhere in my Google Drive, but nonetheless, I'm going to download it. File save as, and let me put it as here in, not in documents, PA2 places data. Okay. And so I'm going to read.csv. Okay. And I close that one. So file, let me go there. You all know how to do this one. This property is tells me about location. So I put the location here because of it is Windows file. I'll put this double slash, and I do backslash classes.txt. Okay. Sep is tab, right? I think it is. Tab has to be done differently. So let me do one thing. I think tab.
Do you have to say how it's separated?
That's what I'm saying. Separator is, I think I have to do this. Let's see. Otherwise, I have to go back. So these are all the things, or I have to read. Yes, you have to say that. We can try without that. Sometimes it figures out itself. Let me try without that, because it did read. Okay, but I don't know whether it is correct or not. So I have to store it and open it and see. Okay, it did read. Oh, okay, but the names are not there. Okay, so I have to say. The first one is it took it as name. That is the problem. Okay. So we have to say all those things. Okay. So let me do one thing. Person grade.csv. So it tells you header is not there, right? So false. We have to say false. So let me say p is equal to I read it there, but I have to say header is false. Now, and then I can attach the names later on. Okay. So view, now I have everything. Oh, but it says only one variable. It's a problem then. This is running as one variable. So this is not working. So let me do a few things. Here, code separator. Separator is correct. That is correct. I don't know whether you are seeing this. This is the tab. So header is, that is okay. It worked out all right. Code, data fields to comment clear. This is fine, but still it is taking it as one variable. So I think it is not. It's not a tab. That's
What
not
if we say header is true?
No, header is true means it. I think that is okay. Let's see. It's the same thing, right? How the output came at the top.
Mm.
So it's not a, it's really false because there is no header there. And then we have to assign the column names, okay? But
Okay.
here is the separator is fine, but what is happening is, okay. And then I can attach names also in one, and or I can do it later. Column names, a vector of optional names. Default is to use V, but it is not taking multiple values. That's where the problem is. Okay. So we have to do why it is not taking backslash. It is correct. Backslash is tab. Fill skip column names. I will give that later. Separator is comma backslash read delimit. See, I should use this one. Read dot delimit. That may be the issue. Okay, and then I have to use column names is equal to. Let's give the names there. Not here. I know it here. Let's do it this one. Okay. I will say climate and CNT. CT, climate and terrain. Okay. Housing, healthcare, health, housing, health, housing, health, crime, transport. Housing, health, crime, trans. Education, arts, recreation, economics. Education, arts. What is the next?
Recreation.
Recreation and economics, right?
Economics. Yes.
Create. Something has happened here. There is something mistake. That's why it was not doing well correctly. So there must be a one code here. Econ. So these are the things. Let's try. Okay. So now it is split. Oh boy, no. Something has happened.
Mm.
It has taken the first value, separator, header, false. I don't think it is a tab. Tab means it will be exactly the same. It's space. Maybe let's see the space. There's no space. Okay, you know what I will do? So I'll do this. CSV. No, Excel. I'll store it as CSV. Okay.
Okay. Better.
These are all the things that you have to know. You know, in real life, this is what will happen. Okay. Text columns. Fixed to it, delimited, not fixed to it. Next. Space. This is what I wanted to do. Finish.
Okay.
But there's a problem in the first one. I will take care of it later. See this one. Okay. Now I save it as save as IOAP2. Probably it is there. File that file. I don't know. Okay. Places .csv. Okay. So let me see whether it's stored correctly. There might be a problem. That's why. So it's called. It is written like this. So I didn't write it. Save it correctly. So save as. You have to think all these little details. Okay. So let me open this. File save. Copy. See, I should have put within parentheses, within quotes. Then I don't have to go and select that. Then it will be perfect. Okay, this name won't work because use a name that does not include, I don't need a CSV there. From dot, that was a dot was giving the problem. Okay. Oh no, wait. Maybe I'll just do it like this. It's easy. Why bother? So now it should work. Okay. Save it. That's what places the name won't work. They use name that does not include character. Oh yeah, of course I don't. I have to take out those.
Quotes. You can
Oh,
say
yeah. Not
quotes.
here. I should not do it here. In a different place I can do that method. Okay, because it's now it is CSV is included. Now it should be okay. So okay, clean up this. You can see FA2, not FA2, places CSV. Okay, so now you go back to the R, same directory. Okay, so .csv. Everything else should be here, but I should say here, comma. What it is, something is going on. I don't want this data set actually. Why is that it keeps coming to me? I don't want that data set. So P is read like this. Header is false. Column names. I think it is this. I'm going to attach it later on. Okay, names as this. I'm going to take it out. Control X. No, oh, because I can't do it. X. Okay. Okay, save view. That still is a problem. Why is that? Maybe I didn't store it correctly. I did store it correctly. Save as, maybe I didn't go through.
Is there two different CSV type?
Let me see. Now I did redid it. Okay. Documents. Not document PA2.
I think that there's like a two different CSV type, and you have to choose the right one.
It's okay. It should work. Hold on there. Okay. P is equal to P.csv. I know, but I don't use usually second CSV. Should work. I don't know why, but let me see. Oh, I have been giving text. That was the problem. Okay. I wasn't using CSV. See, this should be CSV.
Yep.
Okay, now I need to attach names, right?
Yes.
Column names for P is equal to this one. I'm going to give that. Okay, then it should work. See, oh, I should do it this way. Oh boy. Okay. Sometimes it works, sometimes it doesn't. Still a problem. What is it? Error in column names. So, column names. Let me see what is going on. Column. Oh, it should not be a dot. Huh? Is that what it is? These things worked before, so I'm kind of adamantly following that. Let's see. Okay. Okay. Now I got it. Everybody is good?
Yes.
sir. Yeah.
This is
Yes,
very
sir.
important. Don't
Yes, sir.
undermine what we are doing, because these are the things you will face in real time, in real life. Okay, real work. So let's just
Yes,
finish
sir.
this one.
R is very finicky.
No, all programming languages are like that. So I'm going to do the covariance. Remember this? Sorry. Remember this. This means covariance. Find the covariance for all the places. The first, all the 9 variables. Okay, I take the columns, right? The first 9 are variables, right? Places. Then so actually I have used it at P. P is my data set, right?
Yes.
I call them as eigenvectors. U is all eigenvectors. D's are all eigenvalues because I'm taking eigen and then I'm taking the the object entity values. Then I can diagonalize it, and then I can do all this matrix multiplication, and then proving that if I take the covariance matrix and if I do the eigenvalues decomposition and if I multiply all those things together, it should come back to my covariance, isn't it? Everybody understands? Do you understand what I'm talking? These are the eigenvalues. This is the eigenvectors, and then is the transpose of eigenvectors. So I diagonalize it. So that means every value is going to the matrix scalar multiplication to this part alone. Everybody understands that part? Please write it down and do it as a homework. This one. That is, if I have eigenvectors and eigenvalues, I diagonalize the eigenvalues and then put it in the middle, and then multiply on the left with the eigenvectors, right to the transpose of eigenvectors. This will come back to this will come back to the covariance matrix. That's what the eigenvalue decomposition says. This is same as this. That is same as the following. I'm going to show it to you. Okay. This decomposition formula is that one. That's what I'm trying to say. The decomposition formula can be written like this in the matrix form. Get it?
Yes, sir.
Form. Okay. Think so. Okay. That's what I want you to do as a homework, Nene.
Okay.
So just please write it down. It's a very important conclusion. I'm going to, this number is 97, slide 97. We'll come back to that 97. Okay. This is 39. So I'm saying this part is actually can be written in a matrix form. Okay. The eigenmatrix, which is all eigenvectors together, times the eigenmatrix transpose. But in between, I have to put the diagonal matrix of all the eigenvalues. The diagonal matrix means all the values are 0 except the diagonal values. Understand?
Yes, sir.
Can you verify that and prove yourself that the whole thing can be written in matrix notation as the eigenmatrix, that means all the eigenvectors times diagonal of the eigenvalues times eigenmatrix transpose. Everybody got it? It's a very important notation. People use it, and so I'm going to write it down here. So let me put it this way. Yep, sorry, I didn't mean that. Undo. I meant this. That is eigenvalue decomposition. Can you please remember this? Eigenvalue decomposition can be written in matrix form as eigenmatrix star. That is multiplication, right? Diagonal matrix of eigenvalues. Everybody understands this part? Times
Yes.
eigenmatrix transpose. Everybody is good?
Yes,
Yes, sir.
T is transpose. Okay. So this is another way of the simple way of writing this is this. That's what I'm saying. Okay. So I have come to now 96. So what I'm trying to do is, in between I'll come back. Don't worry about it. There are a lot of notes we'll cover. But in 96 I have that notes about places or greater harmonic. That's why I'm going there. Okay. So very interesting notes I'm making there. I'm saying, okay. So if not 97, this one. Okay, not this one. This one. Okay. So these are the eigenvectors. These are the eigenvalues. That's why I'm saying the eigenmatrix times the diagonalized matrix of the eigenvalues times transpose of that should be equivalent to the covariance matrix, isn't it?
Yes, sir.
So if you do this, it will become a 0 matrix. Can we do that now? It's just these three, verify and show it to you mathematically, in computationally. Okay, and then I will use a package called a function called PRCOM, that is principal components. I just do this, and then it will tell me all the objects in that, and then we can explore that object. Okay.
Okay.
And then we will also do what is called the biplot. The first two eigenvectors in the transform space, how the points are falling in the transform space is the biplot. how the points, original points are falling in the transform space is called biplot, okay? So let us do this. Let's do this one. This will come quickly, just these are, you understood these things, so I'm going to do it in one line, okay? One shot. Oh, U is not defined, something is not correct. U is eigenvalues Y. Oh, places is not defined, of course, places is not defined. So I should do it as, okay, we'll finish it soon, don't we? It is P, remember that, it's not places. So in order not to bother that, I'm going to make it P as same as places. Okay. Now I do Control V, everything is done. You see this one? Everybody?
Yes.
So the
Yes, sir.
the U refers to eigenvectors, D refers to eigenvalues. I diagonalized D only, so this is what diagonal matrix means. I takes the eigenvalues and then puts in the diagonal, rest of them are all 0, okay? And then I am doing this eigenvalue decomposition in matrix form minus the original data, covariance data, everything. This should be equal to 0, isn't it? This difference should become 0 because this is same. This is same as this. Isn't it 0? These things are all 0, isn't it? Because it is e power minus 17, minus 18, minus 19. Just a rounding error. I can show it to you. What is that? I'm sorry?
Nothing, sir.
Yeah. So what I'm saying here is, if I do the rounding, then you will know, yes, it is true. Okay. So let's put this at 2 decimals or 4 decimals. See what happened?
Yes.
So this is another way of writing it. Okay. But let's go back to the another important thing. Okay. The another important thing is, we want to, basically the PR comp is written based on these things only. So, but let's go there because it does some other things also for us. So I'm going to do also, this one is based on log values, okay? Because it is high values, there is too much variance is there. So you take logarithmic transformation. So let's just do this. This one tells you all the objects of PR comp, okay? PR comp refers to the principal component analysis. So these are the things you will say, okay? So yeah, we want to put it like this. Let's do this one. PR, that is principal PCA, okay? PCA. Let's put PCA, not PR. Okay. So PCA has center, rotation, scale, as standard deviation X, original value. Okay. PCA X refers to it should refer to the original value. Okay. No, not star, dollar. This is the standardized value because they are talking about, but everything is done, right? Look here. This is the log value, right? What is it? Log value. Yeah. X refers to the logarithm. Let's finish this quickly, okay? I won't take much time. Another 3 minutes. So this is the centered value. Rotation value refers to the eigenvector. This is the scale. So let me go back to this PR comp. We should just ask what are those definitions, right? Okay. So X for the numeric or complex matrix, which provides the data for that's what it is. It's just the data, right? But the data is logarithmic data, right? So logarithmic data and centered data. So it is not only taking logarithm, it also subtracts the mean. Okay. That's why, a logical value indicating whether the variable should be shifted to be 0 centered or not. So it subtracts the mean values. Okay. That's why it is. And then logical value. So we can find out what the centered values are. Okay. PR comp, not PR comp, PCA, dollar, center, right? So these are the center. So you take the logarithm value and then this is the mean of the logarithm value, you subtract that. That's why you get that. Not only that, you also divide by scale, right? The standard deviation, usually the standard deviation. So this is PCA dollar scale. Okay, it's not, okay, the scale is not used, that's what it says, okay? So some standard defaults are there, so scale is not used. You can use the scale also, okay? Now, the important thing you have to relate is, this is connected to the eigenvalues, eigenvector. Once you do this, a lot of things will come together very quickly for you. That's why I'm spending time about eigenvalues, eigenvectors, all those things, okay? So let's do the, what are the things we have? Formula, center, scale, tail, wrong, okay. What are the things we have here? Let's see. LS, PCA. So rotation. Okay, this is where the eigenvectors come into play. Okay. You see this one? And how many eigenvectors you should have? Technically, you should have only 9 vectors, isn't it? Also called how many principal components? Same thing. That's why you have this principal component 9. And it is connected to these variables. Remember, these are the original dimensions. These are the original dimensions. But if you want only one principal vector, you use the PC1 alone. That's what your rotation is, because it rotates the axis in such a way that most of the variance is explained by the first principal components. Everybody got it?
Yes, sir. Yeah.
The second principal component is like that. Okay. So if I plot all the points projected by only these 2 axes, then that is called the biplot. One more time. If I plot all the points projected by only these 2 axes, take the original points and then project it on these 2 axes only. That becomes your biplot. Is everybody good? Everybody heard of it? Okay, excellent.
Yes, sir.
Okay, that's what we are going to do. And here is, let's quickly do one more for the for the murder data. Okay, and we'll close it. Okay. So scoring essential PC dimensions. So why don't we do that? It's getting late, so we do it tomorrow morning. Okay, 9 a.m. US Central Time. Your time is 7:30 p.m. every India people. Okay. Okay.
Okay, sir.
Let's do this plot, and then it closes PCA. Immediately, quickly, everything will come together, because principal component is the foundations are used all over. Thank you very much, everybody. Have a good night. We'll see you tomorrow.
Thank you, sir.
Thank you, sir.
Okay. Thank you.
Good night.
Good night.
Good night.
Good night.
Good night.